Today's lesson is going to continue on lesson 3.1, but specifically we're going to focus on graphing exponential functions. And so the objective today is to evaluate, analyze, and graph exponential functions. So we're going to be finding domain, range, intercepts, asymptotes, basically everything about exponential functions, but also describing transformations of those. So first off, what is an exponential function? Well, it's anything of the form y equals a times b to the x, where we consider the a value to be considered what's called the initial value. Sometimes in like a exponential growth problem, right, that might stand for the initial population, but the b value represents the growth or decay factor. But this is your base form of an exponential function where, again, the exponent is now a variable. So here's the key concept number one here, just knowing the general shape of both what's called the exponential growth and an exponential decay. So if you have that base form, f of x equals some a times b to the x, if your b value is strictly greater than 1, then we call that a growth, as shown to the left. So that's what it looks like. Notice a key point there that it does cross through is the point 0, 1, because if I plug in 0 for any exponent, right, anything to the 0 is always 1. If the b value is specifically between 0 and 1, so you kind of see a fraction there, or maybe it's a decimal between 0 and 1, we call that a decay function. So let's look at our first example here. So it says sketch and analyze the graph of 4 to the x. So we are going to be finding everything about that 4 to the x. So first thing we want to find is what the domain is. Right? Domain is all the x values that I can plug in for x. If you look back on the graph of this, right, since 4 looks like that's bigger than 1, so this is going to be considered an exponential growth function. So it'll look something like this, right? And remember that y-intercept's at 0, 1, so there's some key things we can already jot down. But looking at the shape of this, those arrows go on forever in both directions. In fact, I can plug in anything for x, right? I can plug in 0, I can plug in negative numbers, I can plug in positive numbers. You're always going to get an output. There's nothing that makes that undefined. So the domain here of any exponential function actually is all real numbers. You can plug in anything, okay? But the range is a little different because notice here on the graph, it does not go below that x-axis, right? So we consider that an asymptote, a horizontal asymptote. So the range is all positive values above the x-axis, so that means everything from 0 all the way to infinity. Intercepts. Well, since it doesn't touch the x-axis, you're going to have no x-intercept, I should say, so there's none there. But there is a y-intercept with these. In fact, y-intercept always happens when you plug in 0 for x, and in this case, if I plug in 0, you get 4 to the 0, which is 1. So the y-intercept crosses at 0, 1. The next thing up on our list is asymptotes, right? And notice the green line represented sort of the horizontal asymptote. If I were to describe that as an equation, that would be horizontal lines we describe as y equals, so that would just be simply y equals 0 would be the horizontal asymptote there. End behavior, there is two directions here, right? We always have two answers for end behavior unless it's like a radical function. But if I talk about end behavior here, I should see this notation. X approaches infinity of f of x. So as x gets bigger and bigger and bigger, as I go this way, it looks like it shoots up to infinity. So in the positive direction, it goes to positive infinity. But notice in the negative direction, as I go this way here from that y-intercept, and as I go to the left here, it looks like it approaches an output of 0, right? It's starting to hug the x-axis there. So the answer for that second end behavior would be 0. And then lastly, where is it increasing, where is it decreasing? Notice with a growth function, your slope is always positive. And so here, increasing basically forever, right, from negative infinity all the way to infinity. Where is it decreasing? Never, or none. There is no intervals on which it's decreasing. So I want you to try this one on your own. You can graph this on your calculator under your Y1, right? And then look based off the graph, see if you can answer all those questions. So you can pause the video, try this on your own, and then we'll take a look at this in a few seconds. Good luck. So if you graph this in your graphing calculator under the y equals, what you're going to notice is, I think the y-intercept ends up being 0, 1 again, but then it's going to look something like a decay function here. So if it's to negative power, it has the same resemblance as like a decay function, where your b value is between 0 and 1. So based on this graph, again, domain of any exponential function is always going to be all real numbers, okay? But the range here, notice, the range again, it doesn't go below the x-axis, so it looks like it's all positive values again. So everything from 0 to infinity. The x-intercept here, again, since it doesn't touch the x-axis, for the x-intercept we would say none, but the y-intercept is when x is 0. So if I plug in 0 for this equation, you get 5 to the 0 essentially, which is 1, right? So it does cross at 0, 1. As far as the asymptotes go, there is a horizontal asymptote, so since it doesn't go below the x-axis, but it hugs it, there's a horizontal asymptote right at y equals 0 here. And then as far as the end behavior, right, we always have two directions. End behavior for this one in the positive direction, as I go to positive infinity, it looks like it peters out, right? It approaches 0. And so in the positive direction, I go to 0. In the negative direction, as I go to negative infinity, it looks like that one shoots up, right? It shoots up to positive infinity there as I go to the left. And so in the other direction, our answer would be positive infinity. And then the last question, is it increasing, decreasing? So notice with this case, in a decay function, the slope is always negative. So it's always going to be decreasing, so forever, negative infinity to infinity. And it never increases. So here our answer would be never. All right, so here's a kind of a big overview of the transformations of exponential functions, but the same rules apply with other functions. So if you notice this column right here, that kind of has the rules and what they're labeled as. So remember, you shift things left or right if it's sort of embedded in a function. So if you see like 2 to the x minus 4, that's taking the function 2 to the x and shifting it, well, if I describe that minus 4, right, that's inside the function, that means left or right, but remember it's always opposite, so that technically would mean right 4 units. Right 4 units from where that 2 to the x was originally from. If you see a negative in the exponent, right, a negative in the exponent, just like that last case, that's a reflection over the y-axis. And then we do see like horizontal versus vertical shifts. So if you see here, we have a horizontal compression with your a values in front. If you have an a value in front, like right here, right, then that would be a vertical stretch. And then the translations up or down, you'll see that on the outside, right? So if you see this example here, that would be taking that 2 to the x and shifting it up 8 unit would be plus 8 on the outside, and then minus 8 would be down 8. So take a moment to at least jot the transformation connections here. And to be honest, I would write the translation and maybe even have those examples in my notes as notes for this slide. So you can pause the video and see if you can copy these down here, but we'll take a look at our last couple examples dealing with transformations. So here it says, use the graph of f of x equals 1/2 to the x to describe the transformation of g of x, and then sketch the graph of that function. So if you graph the parent function here, 1/2 to the x, notice the b value here, that's between 0 and 1. And so that's going to tell me that that's going to be a decay function. So it's going to look like a decay. So if I were to do a rough sketch of this, the y-intercept, if I sub in 0, would still be at 0, 1 there. And then a decay function is going to look roughly like this. So that's what the original f of x would look like in blue here. When I look at g of x, notice the only transformation happening is in this exponent. And anytime you have a plus or minus in the exponent, that shifts things left or right. Since it's plus 1, to describe this, if I were to describe that first part transformation, that would mean left 1 unit. And so that means that entire graph gets shifted left 1 unit. So this 0, 1 now, that 0, 1 point is now going to be shifted left 1 unit at negative 1, 1. The shape didn't change. We didn't have any horizontal or vertical transformations going on, or compressions or shrinks, so looks like it's just going to look like this. The same kind of function, just shifted over left 1 unit. So I want to see if you can try this one on your own. There's a lot of things going on in this one. In fact, I think there's 3 different types of transformations that you should be able to describe here, okay? But once you describe them, I want you to just do a quick sketch of what that transformation graph looks like. So you can pause this slide and try this problem, and then we'll go over this in a few seconds. Good luck. So it looks like we're dealing with the same function, 1/2 to the x, right? So again, it's going to look like the same as our last previous problem going from 0, 1, and it's going to look like some kind of a decay function. So the important part here is trying to describe all that's going on for j of x here. Notice there's a negative in front. And anytime you have a negative in front of any equation, that specifically tells you a reflection over the x-axis. And then notice there's a 2. There's a 2 in front. And anytime you have a coefficient, that a value actually in front, right? If the value's bigger than 1, which it is, 2's bigger than 1, then that's going to be called a vertical stretch. So you're actually stretching this curve a little bit. There's nothing going on horizontally because that's the same equation there. But notice vertically at the very tail end you have that plus 1. And that plus 1 just simply means up 1 unit. So to be able to sketch this, I mean, you have that graphing calculator support, so you can always plug it into your y equals to check if you've gotten it right. So first and foremost, if I shift that point up 1 unit, so that 0, 1 up 1 unit, it's going to look something like this in green. But now if I were to take that and reflect it now over the x-axis, it's going to look like this. And I think if you look on your graph, that crosses at 0, 1. And remember, you can always, if I wanted to get a little bit better than just a sketch, so the answer would be that blue curve there. If I wanted to be a little bit more accurate with my sketch, you can always go to your table feature, right? Pick some nice points out, and you can plot some nice points on the coordinate plane there. But there's the rough sketch of j of x. So that concludes our quick little lesson today. So you can jump onto your MacBooks and complete the homework that's going to be due after MEA break. And if you have any time remaining today, don't forget that you got a couple worksheets out there, that interest formula worksheet, as well as the simplifying expressions from yesterday's worksheet. So take some time to complete those. All 3 things will be due next week after MEA, and hopefully you guys have a great MEA break, and we'll see you back next Monday. Have a great day.